Let's solve Unit 2 Computer System Architecture questions. The instructions evaluates the expression x is equal to a plus b into c plus d. In which of the following? Let's see about all these instructions now. This dot is actually star. X is equal to a plus b into c plus d can be evaluated as 3 address instructions will be in this format. The same set of 3 instructions are given here. What is this actually? Get the value of the operand A from the memory, operand B from the memory, sum them up and store in register R1. Similarly, get the content of C from the memory, content of D from the memory and sum them up, store it in R2 register. Multiply the values in R1 and R2 and store it in the memory under the name X. So this is the explanation of those instructions. There are 2 processor registers R1 and R2. These are the processor registers. M of A denotes the operand at memory address A. So from these 2 memory address, we are taking the operands and summing them up to store in R1. Similarly, we are taking up these 2 operands and then summing them up to store it in R2. The values in R1 and R2 will be multiplied and then stored in X. We can say that the instructions are 3 address instructions. Option number 1 will be the right answer. The same expression can be expressed in 2 address instruction format, 1 address instruction format, 0 address instruction format and RAC instruction format. I will now show you all the formats so that it will be a good learning for you. These are the 2 address instructions. Here you will have only a register and 1 memory address involved here. So we are moving the memory address A to R1 and then inside R1 you are adding it to the memory address B. These 2 operations will hold the value of A plus B. What is the MOV instruction? This transfers the operands to and from memory and processor register. Similarly, for C and D, we have 2 instructions. MOV, the contents of C to R2 and then add the content of D to the existing value in R2. This 2 will give A plus B. This 2 will give C plus D. Then these 2 will be multiply the values in register 1 and register 2 and move the result to X. So this is why we mentioned multiplication first and then MOV instruction next. Let's see the 1 address instruction format. In 3 address we had 1, 2 and 3 address totally. In 2 address we saw 1, 2. 2 address in total. Now there is only 1 address involved. Load A, add B, store T. What is the variable T here? Address of a temporary memory location required for storing the intermediate result. So far we have been working with A, B, C, D and X. But in 1 address instruction we have a new term T. That's why I told what is the T. It is for intermediate result. Now we are loading A to the accumulator. We are adding the content of B to the already existing value in the accumulator. This is similar to the instruction given here. But there we are involving register and in 1 address instruction we are involving accumulator. We are moving the intermediate result to a temporary storage. That's why we mentioned store. Then we are loading C, adding D. Accumulator is having the result of C plus D now. The next operation will be multiplication. Already T has the value of A plus B here. So now we are multiplying T, that is A plus B, with the accumulator value and from the accumulator we are storing it in the memory address X. The same expression is evaluated in 1 address instruction in this way. Now let's see 0 address instruction. Here this is done with the help of a stack. TOS is the top of stack. They are pushing A to the stack. Let's have A. Then they are pushing B to the stack. Then they are adding. It means we are giving an operator here and this becomes A plus B. Similarly, we are pushing C to the stack and then pushing D to the stack. Similarly, adding C plus D. So when you take the stack now, A plus B evaluation will be here, then C plus D evaluation will be here. Now we are multiplying both these values with the operator into. After multiplication, the result will be present here. That result will be transferred to X. So we are popping X in the final stage. If you use an accumulator, it becomes one address instruction. When you use a stack, it becomes zero address instruction. Two address instruction involves MOV instruction, and in three address instruction you have only the operation related instruction. Next we will see about RISC instruction. Reduced instruction set computer is RISC. We are loading the content of A to register, B to register, C to a register and D to a register. We are adding the contents of R1 and R2, that is A and B, and then storing it back to R1 itself. From this particular expression you can understand that this is actually R4. We are adding R3 and R4 and storing it in R3. So R1 has the value A plus B and R3 has the value C plus D. We are multiplying R1 and R3 and then storing the result back in R1. This is what is given here. This R1 result is now stored in X. When load and store instruction is using two parameters, one with the register and one with the memory address, then you can call it as RISC instruction. When load and store command uses only the memory address, it becomes one address instruction. What is actually load here? Load instructions transfer the operands from memory to CPU registers. Next question, regarding the subroutines, see the following sequence of tasks to be performed. A set of common instructions that can be used in a program many times is called a subroutine. A function, we can say in programming aspect. The service routine must have instructions to perform the following tasks. This will be the sequence of tasks. We have to save the contents of process registers first. Check which flag is set. Service the device whose flag is set. Restore contents of processor registers. Turn the interrupt facility on. Return to the running program. Now we will rearrange this. Save the contents of processor register is C. Check which flag is set is D. Service the device whose flag is set is B. Restore contents of processor register is E. Turn the interrupt facility on is A. Now just see the sequence C, D, B, E, A. Option number 3 will be the right answer. Where is this topic available in the book? In Programming the Basic Computer, you have a major topic called Input-Output Programming. Under that, there is a subtopic called Program Interrupt. Under that content only, you can find these 6 tasks in the reference book. Next question. A computer system with cache access time of 100 nanoseconds, a main memory access time of 1100 nanoseconds, a hit ratio of 0.9, then average access time would be. In memory hierarchy, you will have secondary memory here, that is for storage. Then above that you will have main memory, and inside the main memory you have something called cache. So whatever you need to process will be taken from the cache memory. In case if that content is not present in the cache, it will be fetching it from the main memory and then storing it in cache and then go for processing. This is what will happen when we are going to fetch something that is not present in the cache. They have given the cache access time as 100 nanoseconds and they say the hit ratio as 0.9. It means 90% of the time the content is accessed from the cache memory and 10% of the time it is accessed from the main memory. What are the given values? Cache access time is equal to 100 nanoseconds and main memory access time is equal to 1100 nanoseconds. So this main memory access time can be also taken as the physical memory, the RAM part. When the process is going to take the data directly from the cache, you have a value called 100 nanoseconds and 90% of the case this is going to happen. For the remaining 10%, this cache has to fetch data from the main memory, and the main memory data will be transferred to the cache. After that only it will be used by the processes. In that case, you have to find the memory access time. They have given hit ratio as 0.9, which is actually 90%. From there we can get the miss ratio as 0.1. So 100 minus 90 will give 10. What is 10%? 10 divided by 100, which is equal to 0.1. When it is given in 0.9, subtract 1 minus 0.9 to get the miss ratio. When they have given in percentage, subtract from 100 and then apply the value. So here it is 0.9, that's why we are taking 0.1. So this is what I explained here. 90% of the time the cache memory will be accessed. Remaining 10%, the main memory has to be accessed and the contents has to be transferred to the cache, and this time will be totally called as memory access time. So what is the memory access time? You have to access the physical memory and then place it in the cache. So let's substitute the value. For physical memory, we are going to take this 1100, and for cache access time, we are going to take this 100. So 100 plus 1100 will make 1200. For the remaining 10% of miss ratio, we will take 1200 nanoseconds to access a particular content. So when it is cache memory, it is 100 nanoseconds. When it is other than cache, we are going to go for 1200 nanoseconds. This is for 0.9 hit ratio and this is for the miss ratio. So this can be called as memory access time or average memory access time. But here I am just keeping it as memory access time. Now how do you find the average access time? Average access time is equal to hit ratio into cache access time, because 90% of the time you are going to access it using 100 nanosecond plus miss ratio into memory access time. The missing part multiplied by the memory access time that we have found here. Now let's substitute the value. What is the hit ratio? It is 0.9 into 100 nanoseconds. This is going to be hit ratio into cache access time plus what is the miss ratio? It is 0.1 into what is the memory access time that we have calculated? It is 1200. You can either call this as memory or average memory access time. Now let's calculate 0.9 into 100 will give you 90. That is, you have to get 900 and then keep a point here, remove the 0 and then place 90. Similarly for 1200, just have 1200, there is only one point here. So you can remove this and bring this to 120. When you add these two numbers, you will get 210. Option number 3, 210 nanoseconds will be the right answer. So you have to understand why we are adding these two terms. When there is cache memory, you access it directly. When it is in main memory, you have to access the content and place it in the cache, and only then you can access. So this time along with this time has to be summed up to get the access time of the memory. Next question, the I/O methods in which memory addresses and I/O addresses are distinct is called. We will see a set of statements and then we will mark the answer. With memory mapped I/O, that is option B, there is a single address space for memory locations and I/O devices. When the address space for input-output operation is isolated from that for memory, this is referred to as isolated I/O. This statement is actually matching the question. The address space for I/O is isolated from that for memory. Actually, it is isolated I/O. The option that accompanies A is B. So, in this case, most of the people are marking option 1 as the right answer. But here, there is a difference between memory mapped I/O and isolated I/O. Here, there is only one address space present for memory location as well as for I/O devices. But here is the isolation happening. Isolated I/O is where it becomes distinct. So in this way we are going to mark option 1 because only isolated input output and memory mapped input output are coming under this category. The rest of the options are totally different from the question that is asked. What is strobe control? This method employs a single control line to time each transfer. The strobe may be activated by either the source or the destination unit. Here there is a disadvantage. Source does not know if the destination has received it, and the destination has no way to know that the source has sent some data. Here we apply the handshaking method to solve this problem. How does this solve? It's by introducing a second control signal that provides a reply to the unit that initiates the transfer. Handshaking method becomes a solution to the problem created by the strobe control method. Regarding interrupt, we have 3 ways. Programmed input output, where there is no direct access to memory. Interrupt initiated IO, which uses the interrupt facility, and we have direct memory access DMA. Now let's see under which category these statements come. The last 3 types, programmed IO, interrupt initiated IO and DMA, belongs to modes of transfer. The strobe control and handshake method belongs to asynchronous data transfer, while memory mapped IO and isolated IO belong to IO transfer. So the IO methods in which the memory addresses and IO addresses are distinct will be isolated and memory mapped as per this option. These two can be called as IO transfer methods. So from there we can map this particular term. Next question, techniques for performing IO. Let's see the modes of transfer. Data transfer to and from peripherals may be handled in one of 3 possible modes. In some books they have mentioned it as techniques for IO operations. That's why the question is asked as techniques for performing IO. In Morris Monroe book we have seen the terms modes of transfer. But in certain computer architecture books it is mentioned as techniques for IO operations, and under that they have mentioned programmed IO, interrupt initiated IO and DMA. What is programmed IO? Transfer of data is between CPU and peripheral. In interrupt initiated IO, it uses the interrupt facility to transfer to and from connected IO devices. In DMA, it transfers data into and out of the memory unit through the memory bus. From here we can say A, B and D are the right answer. Option number 2, A, B, D only will be the right answer. Along with that, we will see another statement. The input-output processor can handle many peripherals through a DMA and interrupt facility. Next question. For making a memory of size 2048 into 8 bytes by using the chips of size 128 into 4 bytes, the number of chips required is, you can see both the units are bytes here. What are the given data? The size of the memory 2048 into 8 bytes. The size of each chip, by using the chips of size they are given, so it is 128 into 4 bytes again. Now we have to find the number of chips. It is given by size of memory divided by size of each chip. We can take this as 2048 into 8 bytes divided by 128 into 4 bytes. Bytes and bytes will get cancelled and 8 will be cancelled for 2. 4 ones are 4 and 4 twos are 8. What about 2048 divided by 128? 128 into 1. You have 14 here. This will be 6. You have 9 here. This will give 7. So 7, 6, 8. We'll try with 6. 8 6 are 48, 2 6 are 12 plus 4 it is 16, 1 6 are 6 plus 1 it is 7. We can mark this as 16. So what is the numerator part? 16 into 2, which will be 32 finally. How many number of chips are there? Option number 3, 32 will be the right answer. Next question, which of the following are sequential circuit? Some are sequential circuits and some are combinational circuits. Let's see. Flip-flop counter belong to sequential circuits. A and C belong to sequential circuit. Option number 2 will be the right answer. What about multiplexer, decoder and adder? These three belong to combinational circuits. Combinational circuit will describe about adders, half adder, full adder, and then under digital components topic as per UGC NET computer science syllabus, you will have the topics of decoder and multiplexer, while adders will be discussed under digital circuits. Next question, arrange the following from fastest to slowest in terms of speed they have asked. Now let's see a memory hierarchy diagram from one of the books. Tape is here, disk is here, main memory is here, cache is here and registers are here. Along with that, they have given with respect to storage capacity and with respect to access time. So access time is where we have fast and slow access. That will actually define the speed. CPU registers are present in the top. So they will be the fastest in speed. Even when you take the access time, they have the term faster. So in this case, C comes first. We have to arrange from fast to slow. So this will be fastest and this will be the slowest. After CPU registers, you have something called main memory. Under this you have SRAM and DRAM, static RAM and dynamic RAM. SRAM is faster and more expensive, while DRAM is slower and less expensive. Since they have mentioned faster here, we have to place SRAM first with the option B, followed by DRAM option A next. Why are we placing both the RAMs together is both belong to the part main memory. Magnetic tapes and hard disk belong to secondary storage devices. Now regarding D and E, if you take as per this diagram order, E should come first and then followed by D. This should be the actual order, but in no option you can find that. Tape is faster than disk when performing streaming read-write operations. In that case, they say tape is faster than disk. That's why we don't have this order, but we have D first. Tape is first in terms of speed and then comes disk in the last place. So this applies to the slowest and this applies to the fastest. So in that case, C, B, A, D, E. Option number 2 will be the right answer. Hard disk seems to be faster than magnetic tapes, but they have given a supporting statement that tape will be faster than disk. That's why we are marking D first and E next. So C comes first. Between A and B, you have only one option with B and A. With this itself, you can mark option 2 as the answer. Next question, the instruction LD, address of X which is equivalent to, accumulator is equal to memory of ADR plus XR is in which addressing mode they have asked. You can find the exact instruction here. This is actually index addressing. So we can mark option number 3 as the right answer. Now let's see about the options. Direct address mode is the effective address is equal to the address part of the instruction. That's why it is direct addressing mode. What about indirect address mode? The address field gives the address where the effective address is stored in memory. So we have seen some diagrams. The address will contain the address of the operand and you have to refer another address to get the operand. If you want, you can refer videos of previous year questions for depiction of indirect addressing modes. What about immediate mode? The operand is specified in the instruction itself. Here you can see immediate mode instruction. What about indexed addressing mode? The content of an index register is added to the address part of the instruction to obtain the effective address. So index register is what is mentioned as XR and the address part is ADR. It is added to obtain the effective address. Next question, the least values of a signed and unsigned data type variables requiring 8 bits would be. In signed numbers, you have both positive as well as negative along with 0. In unsigned, you have only from 0 to the positive side. Negative numbers will not be counted there. So let's see about the signed data first. The range of numbers that can be represented by n bits in 2's complement form is -2 power n minus 1 to 2 power n minus 1 minus 1. This is -2 the whole power. What is here n? N is equal to 8. So 8 minus 1, 2, 2 power 8 minus 1 minus 1. Minus 2 the whole power 7, 2 power 7 minus 1. 2 power 7 is equal to 128. What is minus 2 power 7? This should be minus 128 because till power 6 minus into minus, minus into minus, minus into minus will be plus. And for the 7th power, it will again turn to minus. 2, what is 2 power 7 minus 1? This is 128 minus 1 which is equal to 127. So the range will be between minus 128 to 127. Regarding the question, they are asking for the least values of signed and unsigned data type. Least means what is the smallest value? Minus 128 will be the least value in signed type. So which options are having minus 128 in the first place? Option 2 and 4. So we can rule out option 1 and 3. Now let's see about the unsigned data. I think this will give you a better clarity for 2 power 7. If we say 8 bits, it has to start from 0, 1, 2, 3, 4, 5, 6 and 7. Altogether you will have 8 bits here. So we are going to take the range of numbers of these n bits from 0 to 2 power n minus 1. That is 0 to 2 power n value is actually 8 and minus 1. What is 2 power 8? It is 256. 2 power 8 minus 1 will be 256 minus 1 which is equal to 255. So this will be 255. This is the range out of which we have to pick the least value. 0 will be the least value. Which option is having 0? We will rule out 2. We will go with option number 4. Option 4 minus 28, 0 will be the right answer. This stands for signed type and this stands for unsigned type. Totally there are 256 values. But in signed part it ranges from minus 128 to 127. In unsigned part it goes from 0 to 255. When you add these two, you will get 255. Along with that you have to add one 0 value also. So totally you will have 256 values somehow. Next question, match list 1 with list 2. Let's start with complement first. In the previous question we saw the signed numbers or unsigned numbers are represented in 2's complement representation. So why are we actually using complement? We are using to represent negative numbers. A will be mapping to 3. A3 is available in 2 options. Rest of the options can be ruled out. What about XOR? XOR gates or exclusive OR gates are used mainly to build circuits that perform arithmetic operations and calculations, especially adders and half adders. You can map B to 1. B is 1 here, so we can also rule out option number 2. What about accumulator? Accumulator is a type of register for intermediate storage of arithmetic and logic data. Arithmetic and logical operations will be mapping to accumulator. C is mapping to 4. What about the control unit? The CPU's control unit decodes the program instruction once it is loaded into the instruction register. So decoding work is done by the control unit. D is mapping to 2. Option number 3 will be the right answer. With this, we are completing Unit 2 solutions.